Hey, we'll talk a little bit about radioactive isotopes, just looking into them, kind of what does the numbers stand for, what does the half-life mean, just kind of an intro to this to get us started. First off, one of the more confusing things for a lot of people are these numbers here. So here we have carbon-14, we got thorium-232. What are these numbers? What do they mean? You also may see them, you might see something like 14C with the number, in the top left superscript of that. All this number is the mass of the atom, the mass of the isotope. So typically, typical carbon atom on the periodic table has an atomic number of 6 and a mass number of 12. So when we deal with these, and we're trying to find protons, neutrons, electrons, we're trying to kind of identify the pieces of the atom, this is what we're accustomed to using. This will tell us that, the atomic number, there are 6 protons. So that the atom is neutral, we would need a balance of charges. So this would tell us that there are also 6 electrons. And then finally, we know that this mass number here, this tells us the total atomic mass units inside the nucleus. There's only 2 things in the nucleus, protons and neutrons. We already know how many protons there are. So if we know there are 12 total things in the nucleus, 12 atomic mass units in the nucleus, then 6 of them are protons, the remaining must be neutrons. So if there's 12 total, 6 are protons, you can kind of do 12 minus 6 to figure this out, then there's also going to be 6 neutrons. This is how we tend to deal with these. If we were kind of dissecting this radioactive isotope of carbon, carbon-14, the 14 is the mass. So we would no longer use this mass anymore. We would use 14. Carbon.
Miss Bob, please report to the front office.
Carbon will always have the base of 6 protons. If it doesn't have 6 protons, it's not carbon. It's another element entirely. As long as we're dealing with our neutral form of carbon, which we will mostly, unless you hear the word ion, there will be equal numbers of positives and negatives. Now, if we're dealing with carbon-14, right? If we're dealing with this carbon-14, 14 carbon, we know this is an isotope, which means it has a different amount of neutrons, it has a different mass. We got to use this mass. And we're going to end up, there's 14 total things in the nucleus, 6 of which are protons, which means there must be 8 remaining neutrons. These are isotopes only because of this. These neutrons are different. There's 6 protons, there's 6 electrons, everything is identical about the carbon. Just this version of carbon is a little heavier, has a mass of 14, the top AMU, right? And this has a mass of 12. So when we need to pay strict attention to that if you're discussing the atom in terms of protons, neutrons, electrons. So when we're dealing with half-lives, these numbers, you'll see these numbers a lot following the word. Carbon-14, thorium-235, argon-39, whatever else. Uranium-232 or something, no, I don't remember what it is. 46, anyway. You're going to see these numbers. You're not going to use these numbers in your calculations. This is like, my name is Matt, all right? I can think right now, our AD, several other people in this building are also named Matt. I think 4 actually. So you can't just say Matt and know what we're talking about. You know who's who. You need something more to identify them. So I am Matt Hyde. So you know exactly who you're talking about, which Matt to go to in the building. Whereas if you just said Matt, you wouldn't really know. You go one of 4 places here. That is the role these play in these half-life word problems. Is, hey, this is not carbon, carbon-12 as you're used to it. This is the isotope of carbon, carbon-14. Hey, this ain't thorium, right? Don't go see thorium. Go see thorium-232. So it's identifying it as the radioactive isotope. When we look at the radioactive isotope, we have something called a half-life. Right? The half-life is the amount of time it takes for half of the radioactive nuclei to decay or to transmutate into something else. Now, it's important to know that they don't all decay at the half-life. So it's not like, all right, the half-life of carbon is 5,730 years. So if you have some carbon-14, it doesn't wait 5,730 years and then all of a sudden half of it decays. Whether it's random, right? It's spontaneous and it's random, meaning, 100 atoms might decay today and transmutate into something else. None of them may decay tomorrow. 732.8. We can't have decimal, but you get my drift. So it can be different every day, random and spontaneous. But over time, with the law of averages, right? The half-life tells us how long it takes for half of them to decay. And they might do it at different rates from day to day, but over a long period of time, we can be confident of how much will decay. We can use this to track the ages of things, to track how long something will last. With medicines, to track, how long can we store this medicine in certain conditions? What's the half-life? There's several different uses, but the basics is, we have a mass of a radioactive isotope. This tells us how many neutrons are there, what size the nucleus is. Then we have our basic half-life here. This is going to tell us how long it takes for half of the radioactive nuclei to decay. All right, so I got some more videos coming at you about this. Check them out, and we'll start to use these numbers a little bit. See y'all in the next one.